Hello, I'm going to present a work called Modeling of Fluid Transients into Viscoelastic Compliant Pipes. So it's really good to start a presentation like that with a justification. So fluid transients are generated by abnormal and normal operations in pipelines, but they just not happen. Major concerns about these flows is caused by the appearance of larger pressure loads than those found in the static regime, and the magnitude of the pressure loads and their attenuation and dispersion depends on the fluid and flow nature and the mechanical response of the tube. So an accurate analysis to the design of safe pipelines is conditioned to the joint description of all these aspects. So shortly speaking, some effects, known effects that happen in the transient flow were disregarded because of the complexity of the modeling. It was, for example, an elasticity of the compliant pipe, for example, viscoelasticity, mechanical behavior of the pipe, fluid transient friction. But those phenomena, effects, are known to add dispersive and dissipative effects on the fluid pipe system. So, example, the analysis of the fluid. Classically, they use the quasi-steady friction modeling. That's what that means. That means that they use the same equation for fully developed flows to model the transient flow. For the same equation of friction of the fully developed flow to model the transient friction. But as you can see here in the figure in the right, of the pressure response by time, the comparison between the experimental data and this modeling reveals that this kind of modeling overestimates the pressure, and the pressure response are not in phase with the experimental data. And why that happens? Because this kind of modeling can see local and two-dimensional effects that happens on the velocity profile during the transient. For example, you can see this left figure here. Here is the velocity profile before the transient, and here is the velocity profile after the beginning of the transient. So it seems to appear velocity gradients next to the wall, even though the average velocity of the flow is new. So as the quasi-steady friction just is based on the average velocity of the flow, it can't see this friction that is happening here next to the wall. So depending on the type of application, tubes are made of different materials that's giving rise to different mechanical responses. For example, typical industrial pipe systems are made of steel of different carbon contents, and this kind of pipe falls into the category of linear elastic behavior, mechanical response. In sanitary sewer and water supply pipes are constantly made of PVC or polyethylene that falls in the category of viscoelastic mechanical response. So depending on the application, different response of the tube are actually happening. And what is the influence of that on the transient? This work will just give a glance of this effect. So the main goal of this work actually is a conception of a transient flow modeling in which both the transient friction and viscoelasticity are taken into account. How a thermodynamic consistent transient friction model for the fluid developed previously by one of the authors, and to treat the viscoelasticity of the pipe, we will use the thermodynamic of irreversible process with internal variables. So we will take slowly to get all the details of this model. So first, the consequences. We will see the influence not just the transient friction in the during the transient flow, but also the influence of the viscoelasticity in the mechanism of the fluid transit. And as the model is based on a solid thermodynamic framework, we will be capable of computing the dissipation of the fluid on the fluid and on the pipe. This set of characteristics can be used as a sound tool for practical and theoretical analysis of the for further analysis of hydraulics. So the model mechanical model formulation. The standard phenomenon to be analyzed here is a laminar flow inside a slender compliant pipe. The fluid actually is viewed, it's quasi one-dimensional, but it's viewed as a structured mixture formed by structured shell-shaped constituents. That is, this settlement is just to capture those velocity gradients that I showed in the previous slide. In the pipe is assumed to be thick-walled and slender member. The radial and axial inertia is disregarded, and the pipe can be elastic or viscoelastic. If you assume that the fluid is slightly compressible and that the pipe is in the range of a small deformation, in which the deformation of the pipe is into the category of the small deformation, we find those basic equations. As you can see here, it appears the strain of the pipe. The constitutive equations for the pipe are needed because, as you saw in the basic equation, it appears the strain, circumferential strain deformation of the pipe. So to the inelastic behavior, viscoelastic behavior of a material, of a solid is linked with microstructural rearrangement of the material that is directly linked with dissipative mechanisms. So we will, to treat that properly and with thermodynamic consistency, we will use the theory, the thermodynamics of reversible process with internal variables. What is the core of this theory? There is a set of state variables that gives the local thermodynamic state of a material, but beyond the common variables of state of a solid, internal variables are introduced for the dissipative mechanisms that happens because of the inelasticity of the material. And beyond that, you have to postulate two potentials, that is the Helmholtz-Friedrich energy to find laws of states, and a pseudo potential of dissipation to find evolutionary laws. Is that the solid is viscoelastic? We assume that the inelastic response is purely deviatoric. The solid is isotropic. The model of viscoelasticity applied here is a generalized Kelvin-Voigt model. We compare the response of the proposed model with the experimental data of COBEM 2005, in which the radius number is approximately 1,000. And here we put the proposed model for a viscoelastic material and the proposed model for the elastic material. And here is the experimental data of COBEM. So it's clear that the proposed model has similar responses of the when compared with the experimental data. If you compare with the elastic response, you can find faster damping, and delay the response. And it seems to be clear that the last case is not capable of represent the experimental data. Uh, and one of the main reasons of why that happens is because, as you can see here, the dissipation by time, the solid and fluid dissipation that happens in the system has the same order of magnitude. So if you disregard the viscoelasticity of the model, you are losing a lot of information of the transient phenomena. Thanks for your attention. I'm open for any further questions.